Hello world, my name is Comet, and I have a pretty keen interest in computer science theory, data science theory, and mathematics. One of the core principles of computing is the concept of recursion and how it's implemented. Recursion is when you repeat the same function any number of times, and it's one of the biggest reasons computers got so big. The ability to repeat a task any number of times is an incredibly powerful capability, and in this video, we're going to try to explain how it's possible. I'm also going to introduce some concepts taught at my university's Fundamentals of Computer Science course, which involves an introduction into functional programming and Racket. The first thing we must understand is what a function is. I'm assuming you've taken some kind of algebra course and you're familiar with functions like if I say let f of x equal x plus 2. Even if you're a little hazy though, I'll do my best to cover the basics so you can understand as much as possible from this video. A function has one or more inputs, one operation, and one return value. Let's look at an example here. When you unlock your phone, the input is 4 different numbers. The output is whether or not it's the right passcode. The actual unlocking of your phone depends on whether or not the output is true or false. If it's the right code, it'll unlock your phone, otherwise it'll give you an error. While I won't go into constraints and data types too much in this video, it's important to note that well-designed functions have good constraints on their inputs and outputs. For example, your iPhone doesn't allow you to type letters when it expects a number passcode. Now let's think about what is the operation of this function. What would the output of this function be? To visualize it, we can say you enter a passcode in, and that's your input. The operation is it checks whether the given passcode is the same as the expected passcode, and it returns true or false. If it's true, then it unlocks your phone. If it's false, then it gives you an error. Now, what is Racket? A lot of people at my university come into the fundamentals course thinking, oh, I've coded before, or oh, I've taken AP Computer Science. But Racket is a functional programming language, and that's its main distinguishing factor. What does this mean? Well, it's a variant of Scheme, and it belongs to the Lisp family of languages. Lisp is one of the oldest programming languages, and it's still used today to teach computer science fundamentals. Other languages at this time include Fortran and Pascal, and both of those have been antiquated for years now. These languages originated around the 1960s, so you can tell that computers have evolved a lot, to say the least, since the 1960s. The biggest thing you'll notice about Racket and Scheme is that its syntax is very, very different from anything you'd expect it to look like, unless you've dealt with it before. We'll get into this more later into the video. Lastly, I'd venture so far as to say that no other language has had as profound and as lasting of an impact on computing as Lisp has. As I just said, Lisp's contemporaries when it originated were Pascal and Fortran, and very few universities still teach these languages unless you're taking a very specific higher level course. Lisp also influenced the structure and syntax of pretty much every modern day scripting language. Python, Ruby, JavaScript, Swift, you name it, Racket has probably had some kind of influence on it. Now let's talk about functions in a mathematical sense. You think about 4 plus 5, that's an expression, and it always evaluates to 9. 4 plus 5 is never not going to be 9. But now, what if we write this as f of x equals 4 plus 5? Let's not get ahead of ourselves, this is still always going to be 9 because there's still no variable here. F of x will always evaluate to 4 plus 5, which are both constants, so f of x will still always be 9. However, if we change this up a little bit, and we said f of x equals x plus 5, then the output of this function depends heavily on what x is. For example, if x is 3, then f of 3 is 8. x is 4, then f of 4 equals 4 plus 5. So a function is really important because it can change the output depending on the input. That was a mathematical analysis of functions, but now let's get into how this relates to programming. In functional programming, the whole paradigm is that everything is a function. A function, as we said earlier, has one operation, one or more inputs, and one return value. And if you've had experience with object-oriented programming in Java or Python, then you might have dealt with mutation, where you change the state of an object or you change properties of an object. Whereas in functional programming, this is not possible in a strict functional programming language. You are not allowed to change or mutate a variable. You can only return a new variable with similar characteristics. So let's think about how functional programming syntax looks like. If you wanted to add 4 and 5, you wouldn't say 4 plus 5. You would have the plus operator first, and then 4 and 5 as the inputs to the operation. This might seem a little weird, but the beauty of Racket and Lisp is that in a set of parentheses, the first term is always going to be the operation, and everything after that is going to be an input to the operation. So, say we wanted to make this a function, and we wanted to say we want to add 5 to any number as we had earlier. Well, we can't just say x plus 5 because x hasn't been defined. It's like if you just wrote down x plus 5 on a math sheet, it wouldn't mean anything because we don't know what x is. So that's where the lambda comes in. The lambda is an anonymous function where we say that this just means that we can take in a variable x and manipulate it by adding 5 to x. What do we do with this function? What if we want to call it and substitute some variable for x? Well, as I said earlier, the first term is always going to be your operation, and everything that follows is going to be an input. So if we wanted to substitute 4 for x, this would now be our operation, and we would substitute in 4 as an input. Now, just like earlier, we said f of x equals x plus 5. In Racket, we would say define f as the lambda of x is add x and 5. A quick side note, if you've coded before or done any kind of programming before, you might have seen an if statement. An if statement in Racket is evaluated with 3 parameters. It has a condition, an if true, and an otherwise statement. So if, say, we had a variable x and x was equal to 1, then we would return x plus 1. If x was not equal to 1, then we would return x minus 1. Now let's talk about recursion. Recursion is when you can do the same task over and over again, preferably with slightly different inputs. So a good example of this is the factorial method. If you haven't seen a factorial before, it's a number multiplied with every number before it. So, for example, 5 factorial would be 5 times 4 times 3 times 2 times 1. 0 factorial is the same as 1 factorial, which is 1. And now we can think about this in a more mathematical sense, where we think of 5 factorial is 5 times 4 times 3 times 2 times 1, as we established, but 4 times 3 times 2 times 1 is 4 factorial. So we can write 5 factorial as 5 times 4 factorial. Well then, how do we evaluate 4 factorial? Likewise, we can say that 4 factorial is 4 times 3 factorial. Do you see a pattern here? What we can establish is that the factorial method is pretty much the factorial method of the number before it times the number. So if we wanted to evaluate 5 factorial, we would evaluate 5 times 4 factorial. And this is recursion because there's a method that's calling itself. Let's look at how the factorial method is actually implemented in Racket. We say that if n is less than or equal to 1, so if n is 0 or if n is 1, then we're going to return 1. Otherwise, we're going to multiply n with the factorial of n minus 1. So if you substituted in 5 for n, you would get 5 is greater than 1, so we're going to return 5 times the factorial of 5 minus 1, which is 5 times 4 factorial. If you've stuck with me so far, I applaud you. This is the meat of the fundamentals course, and obviously the course is a whole semester long and it goes into a lot more detail, and you'll learn about more advanced use cases of the Lambda function, but that was pretty much the heart of it. The whole point of the fundamentals course is to understand how recursion works, how Racket works, and the beauty of functional programming. Now let's get into something a bit more advanced. On my last day of fundamentals, we talked about something called the Y-Combinator. It's pretty advanced, and it wasn't tested or anything, and at the time I thought it was lame. I didn't really have that much interest in it, but a couple weeks ago I looked at it again, and it really made a lot more sense. As you can see here, there's a lot of characters on the screen, and it might be a bit hard to follow. But if we analyze this a bit more closely, we can just say that y is defining a function. Let's look at this function. This function is defining another function where it's kind of interesting because you see the same function twice. Now, I want to highlight here that you're not doing the same function twice, but instead, you're calling the same function as an input to that function, if that makes sense. So, as we saw earlier, in a Racket expression, the first term is always the operation, and everything that follows is the input. So we're defining an operation as a lambda function here, and the input is the exact same lambda function. I color-coded these x's in two different colors because although they're the same letter, they are not the same value. The x in the second lambda cannot be used in the first lambda. They are two disjoint functions. Now, why don't we try to evaluate this function? What happens if we call y with some function f? Then, we know that the blue lambda is an input to the red lambda. Now we have to evaluate the red lambda, which means we have to call the function f with the two x's, which were the inputs to the red lambda. If we change the colors a bit and substitute in the lambda twice, we can see that we end up back in our original form. This was the original Y-Combinator. So the beauty of this is that, as we can see, in this function here, a lot of times you're not allowed to use a function while it's being defined. So you can see here that we're defining the factorial method, and within the factorial method, while it's being defined, we're calling the factorial method. In a lot of older programming languages, you had to define a function first and then call it within itself, or then call it later. But then that gets complicated because if you define a recursive function, how do you refer to itself without having it defined? And it becomes kind of like a loop of the chicken and the egg kind of situation. So with the Y-Combinator, you can make any function recursive without this boundary. And the way you do that is, instead of defining a function, we define the Y-Combinator, and then we call the Y-Combinator method with an anonymous function, with the function name being a parameter as opposed to a definition. So that's what the Y-Combinator is, and I hope I at least taught you some ways that functional programming is still relevant in the modern day, and I hope you gained at least some kind of appreciation for functional programming. If you liked it, make sure to leave a like and subscribe, but also leave feedback. I want to know if I should speak faster or slower, or if any things weren't clear, so I can use that as feedback if I do make another video.